Hello, my name is Sokari Prabo. I'll be teaching you physics, and the topic we'll be looking at is motion part 1. In motion part 1, we're going to be looking at what is motion, types of motion, relative motion, and simple idea of circular motion. What is motion? Motion is the change in position of a body with respect to time. Now, it involves how things move and what makes them to move. When we are talking about how things move, it brings us to kinematics, which describes how objects move without regard to the forces that cause them to move. And then we will also be looking at dynamics, which deals with the forces that are responsible for motion. Types of motion. We'll be looking at random motion, translational motion, rotational motion, and oscillatory motion. We'll take our time to explain what each of them entails and how you can be able to know the difference between one type of motion and another. Random motion. What is random motion? What will you see to be able to say this indeed is random motion? Random motion describes disorderly, zigzag, haphazard type of movement of objects. When you see an object is not moving without any orientation in no particular direction, then you know that random motion is what is taking place in that movement. It is usually disorderly, it is in a zigzag manner, it is haphazard. Random motion is characterized by no preferred direction, no orientation, and the particles that are involved in this motion can collide one with another. Let's take a look at an example. The objects are moving no preferred direction, no orientation, and you can see they are colliding one with another. These are the characteristics of random motion. All right, let's look at some examples of random motion. The primary example is Brownian motion, which involves the movement of particles in gas. So, smoke particles suspended in air is an example of random motion. And then the motion of gas particles also in air or in a fluid are examples of random motion. This is an example of random motion. If we try to trace the pattern of motion of this particle or several particles inside this system, we will see that this particle will move in this direction, come downwards, move upwards, and in the process pass through where it started from, move this way. Looking at this movement of this particle, it is actually not in any particular direction, not in any particular orientation, not in any particular manner. It's zigzag and it is haphazard. Translational motion. In translational motion, objects are moving from one point A to another point B without rotating. So rigid bodies moving from one point A to another point B without rotating. This type of motion is characterized by each part of the object following same path. And every point in the body remains relatively fixed one to another. So let's look at an example of translational motion. A car moving from Lagos point A to point B. As the cars move, there is what we call translational motion that is happening. Another example is in bowling. When the ball leaves the hand of the bowler, that's point A, and then it moves to the target, that's point B. That's also another example of translational motion. The next type of motion we're going to be looking at is rotational motion. Rotational motion describes the movement where all the points of the body move in a concentric circle. They have a fixed point and all the parts move around that fixed point in a concentric circle. Let's look at what characterizes this type of motion. The centers of the circles all lie on the axis of rotation. We will look at a couple of examples to be able to understand what rotational motion is. The rotation of the blades of an electric fan is an example of rotational motion. As the blades are rotating, it's moving in a circular path about a fixed point. That is an example of rotational motion at work. The earth rotating about its axis is another example of rotational motion. And finally, the wheels of a moving car about the shaft is also an example of rotational motion at display. And then next, we're going to be looking at oscillatory motion. What is oscillatory motion? Oscillatory motion can also be called vibratory motion, and it describes the movement of a body in a to and fro manner about a fixed point. So it moves to and fro from one point to the other, but it is about a fixed point. There are a few things we need to know. During this motion, the direction of motion is usually reversed and returns regularly to its original position. So it moves from the starting point, moves to the next point, and comes back in the opposite direction back to the starting point. What characterizes oscillatory motion? There is periodic movement and there is repetitive movement. When we look at some of the examples, we're going to see what it means to have a periodic movement. Simply put, it's covering the same distance in the same period of time. And it is repetitive, meaning it moves from A to B and returns back to A following the same path. Examples of oscillatory motion. We have the back and forth movement of a simple pendulum. As the pendulum moves to and fro, moving from this point to this point and back to this point, you can see that it's a back and forth movement of a pendulum as it swings. We have a rocking chair on which our grandfathers usually will sit and then rock themselves. Or if you look at a swing, when it moves to and fro, is also an example of oscillatory motion. Another example is a diving board. Someone goes to stand on the board and loads it by pushing it downwards, and then it takes him up and down again before it jumps off, makes a somersault into the pool. That movement of the diving board is an example of oscillatory motion. And then finally, we have the motion of a disturbed mass on a spring. When it's pulled down, moves downwards and then upwards. That motion is repetitive and it's periodic, meaning it happens over a period of time. Moving up at a given time, coming down at a given time, and that is periodic. That brings us to the end of types of motion. Now we will be looking at relative motion. Relative motion is a measure of the change in position of an object. Now that change happening with reference either to a frame of reference or to a point. Now, every object that moves is measured in distance and time with reference to the point from where it departed or with reference to the point to where it will eventually arrive at. So it is a measure of the change of position of an object with reference to a point or a frame of reference. Example of such can be from rest, or a stationary object, or the origin of the x and y axis, or another moving object. So every measurement of the change of position of the object must be made with respect to the frame of reference. When it happens that way, then we're looking at what? Relative motion. Let's look at an example of relative motion to better understand what it is. When a boy is sitting in a bus or in a car, and the car is moving at 120 kilometers per hour, what will be the speed of the boy? Now, the speed of the boy as it relates to the moving bus, the speed of the boy as it relates to the earth, and the speed of the boy as it relates to stationary objects along the roadside. Now, if the boy is sitting in the long bus and the bus is moving at this speed, 120 kilometers per hour, in the moving bus, the boy is still, but the bus is moving at 120 kilometers per hour. With respect to the earth, the boy is moving at the same speed as the bus. So if the bus is moving at 120 kilometers per hour, the boy sitting in the bus is also moving at 120 kilometers per hour. That is why we are always advised in driving our car to put on seat belts. Why? If there is a crash, whoever is inside the car will also move. There will be a reaction. That person will move out of the car at the same speed at which the car is moving at that time. Why? Because the car is moving with respect or relative to the earth. Now, relative to stationary objects, in as much as during the movement it will be leaving stationary objects behind, it will be leaving stationary objects behind at the speed of 120 kilometers per hour. So relative motion of the boy in the bus as it relative to the bus, or relative to the earth, or relative to objects that are along the road. Let's use numbers to see how we can better understand relative motion. If a boy is sitting in that same bus and the bus is moving at 120 kilometers per hour, and the boy stands up from the bus and starts moving towards the driver in the moving bus, and the boy is moving at 10 kilometers per hour. If he's moving at 10 kilometers per hour and the bus is moving at 120 kilometers per hour, with reference to the bus, the boy is moving at 10 kilometers per hour. But with reference to the earth, the boy will no longer be moving at 10 kilometers per hour, but he will be moving at 120 kilometers per hour plus the 10 kilometers per hour that he has. So the total speed with which he will be moving towards the front of the bus to meet the driver will be 130 kilometers per hour. Now, when he begins to move away from the bus driver back to his seat, still at 10 kilometers per hour, with reference to the bus, the boy will be moving in an opposite direction from where he moved forward from. While relative to the earth, it will be the bus moving at 120 kilometers per hour minus 10 kilometers per hour, which is 110 kilometers per hour if he's moving away from the driver. So that is the difference when you are looking at relative motion when it comes to a boy in the bus moving towards the driver or moving away from the driver. We're going to be looking at simple idea of circular motion. A circular motion is the movement of an object along the circumference of a circle, or rotation along a circular path. So this motion takes place along the circumference of a circle or rotation along a circular path. Usually the motion can be uniform, in which case the speed at which the object is moving along the circumference of the circle is going to be constant angular velocity and speed. Or the motion can be non-uniform, in which case there will be a changing rate of rotation, meaning the velocity and speed will not be constant. Let's look at some examples of circular motion. The moon circling around the earth is an example of circular motion. The earth moving around the sun is also an example of circular motion because it's moving around the circumference of the sun. A stone tied to a rope and swung either horizontally or vertically in a circle is also an example of circular motion. The stone is going around the circumference of the circle. And then planets that are moving around the sun also makes us understand that they are moving around the sun in a circular motion. Now we're going to be looking at the forces that are involved in circular motion. And that brings us to centripetal and centrifugal force. These two forces are the forces that act in objects that are in circular motion. We will take our time to look at what each of these forces are. Centripetal force. Centripetal force is that inward acting force. It is required to do what? To keep an object moving at constant speed in a circular path and directed towards the center of the circle. So when you have a centripetal force, there are a few things you can use to be able to recognize what it is. First of all, it's acting towards the center of the circle, inwards towards the center of the circle, and the object that is undergoing that circular motion, acting under this force, will also be moving at a constant speed in a circular motion. The other is centrifugal force. Centrifugal force is the opposite of centripetal force. How? It acts outward of a circular motion, acting away from the center of the circle. So it appears to act in a circular path and away from the center of the object, from the center of the circular motion. Now let's look at the diagram we have in front of us. This is an object, let's call it A, moving on the circumference of this circle. There is a force that wants to move it away from the circumference and away from the center. That force is what we call the centrifugal force. And then there is another force called the centripetal force that acts towards the center of the circle. Now, both forces are usually equal. That is why you see the object is not falling away towards the center of the circle or falling from the circumference away from the center of the circle. And then we have, of course, the velocity or the speed with which it is moving on the circumference of the circle, usually at a tangential angle or usually tangent to the circle. And then we have the radius of the circle from the center of the circle. Now we can look at a representation of the centripetal acceleration and the centripetal force. A in this expression is the centripetal acceleration, while V is the linear speed or linear velocity, and R is the radius of the circle. And when we look at the centripetal force, F is given by the mass of the object moving in a circular motion multiplied by the square of the velocity divided by the radius of the circle. Let's go through this example to better understand how these two forces can be calculated in a circular motion. First of all, this example says a mass of 20,000 grams is moving in a circular path of radius 40 centimeters with a uniform speed of 50 meters per second. Now we're to find the centripetal acceleration and the corresponding centripetal force. Now, first of all, we're going to look at the items that we have been given. We have been given the mass. The mass M is equal to 20,000 grams. Now we need to change the unit of the mass into SI units. All the units need to be consistent, and the unit we're going to always be working with is the SI unit. And the SI unit for mass is the kilogram. So 20,000 gram in kilogram is 20 kilogram. Next, we're going to be looking at the radius. We're looking at all the parameters that we have been given. The radius is 400 centimeters. And 400 centimeters, we will need to change it to the SI unit. The SI unit is meter. So 400 centimeters is going to be 4 meters. And then, of course, we have been given the speed, which is 50 meters per second. Now, 50 meters per second is the SI unit for speed. So that gives us all the parameters we need to be able to find the centripetal acceleration and the corresponding centripetal force. What did we say is the acceleration? The acceleration is given by v squared all over r. So going with the parameters we have v as 50 squared all over the radius, which is what? 4. So going with this, it's going to be 50 times 50 all over 4. Just to make it a little simpler and easier, if we divide this by 2 and divide this by 2, we're going to have 25 here. And then we divide this by 2 and this also by 2, we're going to have another 25 here. And then 25 multiplied by 25 is going to give us 625. And that is meters per second squared. So that will be the centripetal acceleration for this object. Next, the centripetal force, F, is given by mass times the centripetal acceleration. And that is 20 times 625, which is 12500 Newton. Angular speed. Angular speed is the rate at which an object changes its angle, and it is measured in radians in a given time. It is defined by only its magnitude, and the unit of measurement is radians per second. Take note, it is a scalar quantity, meaning it is defined only by its magnitude. Let's now look at angular velocity. Angular velocity is the rate of change of angular displacement with time. In this case, the velocity is measured or described by its magnitude, which is same as for angular speed, but in addition, it is also defined by the direction of motion of the object. Hence, it is a vector quantity. Why? It is defined not just by its magnitude, but also by its direction. Let's look at some of this terminology in this illustration we have here. We have an object moving from point X to point Y. This object is, the direction of the angular velocity is tangential to the circle. And in moving from X to Y, it covers an angular distance theta. And this is the center. From the center to this point is going to give us the radius. And the distance covered by this object moving from X to Y is S. So the angular speed will be given by omega, which is the angular speed, is equal to theta, which is the angular distance covered moving from X to Y, divided by the time it takes to move from X to Y. And then the linear velocity given by V is equal to omega, which is the angular speed, multiplied by the radius of the circular path. Let's look at a simple example to be able to understand angular speed and angular velocity. A stone is whirled at the end of a rope 40 cm long and makes 10 complete revolutions in 0.1 minutes. What are we to do? Is to find 1, the angular velocity in radians per second, 2, we're to find the linear speed, and 3, we're to find the distance covered in 10 seconds. Now, we will first of all write out what we have been given. We have been given the radius to be 40 centimeter, which is 0.4 meters. And we have been given the angular distance. We are told it's 10 complete revolutions, so it's 10 times it moves around the circle, and the total angular distance in radians of the circle is 2 pi. And so this is 20 pi in radians. And the time we have been given is 0.1 minutes, which is 0.1 times 60, which will give us 6 seconds. Now we know what we have been asked to do. So what is the angular velocity? The angular velocity, omega, is given by theta all over t. And from what we have here, theta is what? 20 pi all over t, which is what? 6 seconds. This gives us 10.47 radians per second. That is the angular velocity in radians per second. Next, we're going to look at the linear speed. The linear speed, V, is the angular speed omega times the radius. And we have found the angular speed to be 10.47 radians per second times the radius, which is 0.4 meters. And that gives us 4.19 meters per second. Finally, the distance covered in 10 seconds. Distance is velocity times time. So the velocity is 4.19 meters per second, and the time we have told is 10 seconds. And that is 41.9 meters. That brings us to the end of motion part 1. But before we leave, let's look at a summary of what we have been talking about. We have looked at basically there are 4 types of motion. The relative motion of a body is based on a point of reference, and centripetal and centrifugal forces act on objects that are in circular motion. Also, angular speed and angular velocity are equal in magnitude but differ in the fact that angular velocity takes into consideration the particular direction in which it is acting, and angular velocity is measured tangential to the circle, same with angular speed, but the difference between angular speed and angular velocity is that angular velocity, in addition to the magnitude, pays attention to the particular direction. Let's round up this session by looking at a simple question. A piece of stone is attached to one end of a string and wound round in a horizontal circle. When the string is suddenly cut, what will happen to the stone? A. Will the stone move towards the center of the circle? B. Will the stone stop moving immediately? C. Will the stone fly off in a direction tangential to the circular path? And D. Will the stone move along a circular path of smaller radius? Obviously, the answer is C, which is the stone will fly off in a direction tangential to the circular path. This brings us to the end of motion part 1. I hope you have enjoyed this session. Thank you for being a part of the class, and I hope to see you when we discuss motion part 2. Thank you, and see you in the next session.